In our last video, we looked at the double angle formulas for sine, cosine, and tangent. We derived those formulas and we used them in different types of problems. Now we're going to look at half angle formulas. We're going to need those double angle formulas to derive these half angle formulas. So let's start with looking at the double angle formula that's in front of us, that cosine of 2 theta, make that bigger, cosine of 2 theta. This is equal to 2 cosine squared theta minus 1. So let's go in here and let's divide each of our angles by 2. So we're trying to derive this half angle formula. So notice when we divided our angle by 2, this is now cosine of theta is equal to 2 cosine squared of theta divided by 2. Minus 1. So since we're trying to derive what cosine of theta divided by 2 is, let's just isolate that on the one side of the equation. So we can do that by adding 1 to both sides. So we would get cosine theta plus 1 is equal to 2 cosine squared of theta divided by 2. Now we can get rid of the 2 in front of the cosine squared by dividing both sides by 2. And then we would have cosine squared of theta divided by 2 is equal to cosine of theta plus 1 all over 2. So we can get cosine squared theta divided by 2. We can get rid of that square by taking the square root of both sides of our equation. So we have to put that plus or minus in front of the 1 square root. And so we get that the square root of cosine squared of theta divided by 2 is equal to the square root of cosine theta plus 1 all over 2. So that gets rid of our square, and now we have our formula, half angle formula for cosine. So we have cosine of theta divided by 2 is equal to plus or minus the square root of cosine theta plus 1. A lot of times you'll see it, let me just write it the way you'll see it, as 1 plus cosine theta. But that's commutative, so 1 plus cosine theta is the same thing as cosine theta plus 1 all over 2. So notice that we have this plus or minus in front of the square root, and that really is determined by which quadrant we're following in. So depends on the quadrant that our half angle is falling in. So not too bad. That is how we derive the half angle identity for cosine. So it's pretty similar to do the one for sine of theta divided by 2. So now let's look at deriving the formula for the half angle for sine. So we're going to do the similar idea. We're going to rewrite the double angle for cosine, but this time we're going to use the one that has sine squared in it. So cosine 2 theta is equal to 1 minus 2 sine squared theta. So again, we're going to go in here and we are going to divide our angles by 2. And so dividing our angles by 2, we can rewrite this. This is cosine of theta is equal to 1 minus 2 sine squared theta of the angle theta divided by 2. So again, we're trying to derive the half angle identity for sine. So let's isolate that term by itself. We could subtract 1 on both sides. And so we get cosine theta minus 1 is equal to -2 sine squared theta over 2. Dividing through by -2, we're going to get sine squared theta over 2 is equal to, so we're dividing by a negative. Let's change the signs in our numerator. Well, let me just show you how to do that. So we have cosine theta minus 1 all over -2. We're pulling basically that negative out front that's in the denominator. And we're going to distribute it to each term in our numerator instead. And then we're going to take the square root of both sides. So we have the square root of sine squared theta divided by 2. This is equal to plus or minus. So this is now negative cosine theta plus 1. So I'm going to rewrite the order. It's 1 minus cosine theta all over 2. So again, this has to deal with that plus or minus, which quadrant our half angle is falling in. And they're almost identical. One is 1 plus cosine theta over 2, and one is 1 minus cosine theta over 2. Both of them underneath the radical. Cosine has the plus, sine and the half angle has the minus in between the 1 and the cosine theta. So let's look at using one of these. So the example in front of us is cosine of 165 degrees. We want to use the half angle formula to find the exact value. I would first look at this to see if I could go about this without using that half angle formula. But if I looked at 165 degrees and I mapped that on the circle, that 165 degrees, my reference angle in here is just 15 degrees, and we're not sure what 15 degrees is. So we're going to use the half angle formula. So what we're doing is we're going to multiply this 165 degrees by a fancy one, 2 over 2 to make this a half angle. So doing that, we have cosine of, so multiplying 2 times 165. That's 330 degrees all over 2. So now I can use this half angle formula. So I have this plus or minus the square root of 1, this is cosine, so it's plus, cosine of the angle in the numerator, so 330 degrees, all over 2. So I need to determine, is that plus or minus in front of the radical? Well, looking at our original angle, 165 degrees, we saw that it fell in the second quadrant. Cosine is negative in this second quadrant. So we're going to use the minus in front of the radical for this one. And so now let's evaluate what cosine of 330 degrees is. And 330 degrees, that's going to get us into the fourth quadrant. We're going to have a reference angle in here of 30 degrees. Cosine at 30 degrees is root 3 over 2. And then we have to think about cosine in the fourth quadrant, but cosine in the fourth quadrant is positive. So we have 1 plus cosine of 330 degrees, which we just said was root 3 over 2, divided by 2. So we don't like fractions within fractions. We want to simplify this. There's a couple of ways to approach that. I tend to like to multiply by the least common denominator of the fractions within the fraction. So that case, that would be a 2, but I can't just multiply by 2 to make it unchanged. I can multiply by 1. And I'm going to write that 1 as 2 over 2. So let's distribute that 2 to each term in the numerator underneath that radical. And so 2 times 1, that's 2, plus root 3 over 2 times 2, that just gives us our root 3, all over 2 times 2, which is 4. So using rules of radicals, I can break that down. If I have the square root of a fraction, that's the same thing as the square root of the numerator, all over the square root of the denominator. So I have the square root of 2 plus root 3 underneath that radical, all over square root of 4, but reducing that square root of 4 is 2. And so we got our answer, and this is our exact answer. And we would leave it in this form. The homework program might ask you for the exact form and then also to estimate it and telling you where to round to. So we have another example in front of us, sine of negative pi 8. It tells us in the problem to use the half angle formula to find the exact value. So we want to rewrite this as a half angle. Again, we don't know how to evaluate sine at negative pi 8. So manipulating it into an angle that we do know how to evaluate is going to help us. And so we want to multiply this again by a fancy one to make this a half angle. And so I have negative pi 8 all over 1. And I'm going to multiply this by 2 over 2. And so when I did that, notice now I have sine of negative 2 pi 8, but we can reduce that. That 2 goes into that 8 4 times. So we really have in our numerator here negative pi 4ths. And then it's all divided by 2. So I'm going to use negative pi 4ths, which is an angle we know how to evaluate, as my numerator, and then divided by 2. So now using the half angle formula for sine, this is plus or minus the square root of 1, it's sine, so it's minus between that and the cosine of my numerator, which is that negative pi 4ths, all divided by 2. So evaluating cosine of negative pi 4ths. So we have 1 minus, well, negative pi 4ths, that's getting me into the 4th quadrant. Reference angle is pi 4ths. I know cosine of pi 4ths is root 2 over 2, and cosine again is positive in the 4th quadrant. This is all over 2 underneath that radical. And let's determine now what sign we have. So notice that we're looking at our original sine of negative pi 8. So negative pi 8 is in the 4th quadrant, but sine in the 4th quadrant is negative. So we need a minus in front of here and not the plus. So we want to clean this up, and we could get rid of the fraction by multiplying by this fancy one of 2 over 2. So we get back negative square root of distributing my 2 on the numerator. I get 2 minus root 2 all over 4. But we know that square root of 4 in the denominator is equal to 2. So we have a negative square root 2 minus root 2 all over 2. So there's half angle for evaluating sine or cosine. Maybe let's look at a different trigonometric function with a half angle. So here we have the cosine, or not cosine, we have cosecant of 7 pi over 8, and we want to evaluate this. It tells us to, again, use the half angle formula. So I don't know what the half angle is for cosecant, whatever that formula is, but I can rewrite this in terms of 1 over sine. Let's just do that first. So this is the same thing as 1 over sine of 7 pi over 8. But this is not one that we know, and it told us to use the half angle. So let's multiply this by a fancy one of 2 over 2. So doing that, we have 1 all over sine of, well, notice when we multiplied that 7 pi 8 by the 2, we can cancel the 2 goes into that 8 4 times. So we're left with 7 pi fourths as our numerator, all divided by 2. So if we look at 7 pi fourths, that gets me down into the 4th quadrant with a reference angle of pi fourths. So now let's use the formula for sine in the half angle. So we have 1 all over the square root of 1 minus, because it's sine, cosine of my angle, pi fourths. Actually, it's 7 pi fourths. All over 2. I forgot that plus or minus there. So let's put plus or minus. We can determine if that's positive or negative right away by looking at, we said that 7 pi 8s, 7 pi 8s. Well, I noticed that that is less than pi, and it's less than pi by pi 8s. And so 7 pi 8s, that would get me into the second quadrant. Second quadrant, so 1 over sine. I know sine in the second quadrant is positive. So in this case, in front of the radical, we're going to use positive, which we don't really need to write, but for right now we will. Okay, so going down and simplifying some more, we have 1 all over the square root of 1 minus, well, cosine of 7 pi fourths. The reference angle is pi fourths. It's in the second quadrant. Cosine is positive in the second quadrant, and cosine of pi fourths is root 2 over 2. All divided by 2. Clearing the fraction in the denominator, we get 1 divided by the square root of 2 minus root 2 all over 4. So same thing as 1 all over the square root of 2 minus root 2 all over 2. So think of this as that 1. It's divided by the fraction root 2 minus root 2 all over 2. Division of fractions, we rewrite as multiplication. First term times, so 1 times the reciprocal on the second fraction. So 2 all over root 2 minus root 2. So I was curious if our answer was left with a radical in the denominator. And so it's not in part of the one answer it is, one answer it's not. So let's just in case you need to know how to rationalize the denominator for this problem in the homework, let's rationalize it. And so we're, again, to rationalize it, we're going to multiply by a fancy one. And we can do that by multiplying by root 2 minus root 2. Root 2 minus root 2 in the denominator. So if we do that, this is equal to 2 square root of 2 minus root 2 all over, well, this is the same thing, square root of 2 minus root 2 times square root of 2 minus root 2. That's two of them, so it's like square root of 2 minus root 2 quantity squared. That gets rid of the radical, leaving us with just 2 minus square root of 2 in the denominator. So unfortunately, this still has a radical in the denominator, and so we need to continue to rationalize the denominator. And we can do it in this case by, because there's more than one term, we're going to multiply it by the conjugate of that denominator. So the conjugate is changing the sign in between those two terms. So instead of 2 minus root 2, we're going to do 2 plus root 2, all over 2 plus root 2. So we have 2 square root 2 minus root 2, all times 2 plus root 2, all over. So this is like a difference of squares. We manipulated it to be that way. So we can square the first term minus the square of the second term. Or if you distribute out, you'll see that you get that. Let's distribute, maybe let's not distribute. Let's just leave it like this for now. So we have 2 square root 2 minus root 2, all times 2 plus root 2, all over, well, 2 squared is 4, minus root 2 squared is 2. So I notice I'm going to get a 2 in the denominator, which is going to be able to factor with that 2 in my numerator. So I have 2 square root of 2 minus root 2, all times the quantity 2 plus root 2, all over 2. And so our 2's cancel, because this was strictly multiplication in between, leaving us with square root of 2 minus root 2 times 2 plus root 2. So our next example in front of us is cosine squared of 1/2 sine inverse of 3/5. So first thing you should do when you're looking at these and see if you can evaluate the inner piece. So sine inverse of 3/5. We don't know what value of sine gives us back 3/5. And so if we don't know that value, then we want to create our triangle. And so we're going to let A, choose some value to equal sine inverse of 3/5. So now if we take the sine of both sides, we get sine of A is equal to 3/5. So creating our triangle, right triangle, if we put A down here in that left corner of the triangle, sine is opposite, which is 3, over hypotenuse, which is 5. And so we want to find this angle over here. Let's call it X, or not angle, side, X. And so we know that X is equal to the square root of the hypotenuse squared, so 5 squared, minus the other leg squared, 3 squared. So this is 25 minus 9, which is, 25 minus 9, which is 16. So square root of 16 is 4. So this length over here is 4. So now let's go back and let's rewrite what we have. So we have cosine squared of 1/2 sine inverse of 3/5, but we let sine inverse of 3/5 be A. This cosine squared of this angle, we can rewrite it if it helps you. This is the same thing as the quantity of cosine of 1 or 1/2 times A, or A over 2, if you want to write it that way. Quantity squared. So we don't know what cosine of A over 2 is, but we do know the half angle formula for that cosine of A over 2. So it's the square root of 1 plus cosine of A all over 2 But then we have this square out here. So squaring this. We would technically put this plus or minus in here, but we're squaring it so it's positive, so we don't have to worry about what quadrant it is in. But we should be able to figure out what quadrant we're in because this is sine inverse. So we know that the range is between negative pi halves and pi halves. It's a positive value, 3/5, so I'm in quadrant 1. So I would have been positive anyways. So now let's looking at this. We squaring the square root. And so this is gonna cancel the square root, leaving us with 1 plus cosine of A all over 2. We could figure out what cosine of A is because we have our triangle. And so we know that cosine is adjacent. So adjacent to angle A is 4 all over the hypotenuse, which is 5. And then this is all over 2. So fractions within fractions, we can clear that. If I multiplied by this fancy 1 of 5, so clear that fraction of 4/5, distribute my 5 in the numerator, I get 5 plus 4 all over 2 times 5, which is 10. So we're getting back 9/10 as our answer. So the next example in front of us is 1 minus 1/2 sine of 2 theta equals sine cubed plus cosine, sine cubed theta plus cosine cubed theta all over sine theta plus cosine theta. It wants us to prove this identity or show this identity. So remember when we're looking at proving or showing an identity, we only work with one side of the equation and we manipulate or try to manipulate that one side to look like the other side. We try to look at sometimes looking at the more complicated side is easier to do. I'm going to work on the left-hand side just because I see that double angle in for sine, and I know that in this section is double angle and half angle. So let's start with rewriting sine of 2 theta. So if you don't remember your identity for sine of 2 theta, this is really easy to quickly do. It's the same thing as sine of theta plus theta, using the sum of 2 angles. Remember that sine of a sum of angle is sine, cosine, sine, cosine. Sine of the first angle, cosine of the second angle, same sign in between for sine, so plus sine of the second angle, which is theta, cosine of the first, which is theta. Those are the same exact things, so this is 2 sine theta, cosine theta, summing those terms together. So let's rewrite what sine of 2 theta is using that. So we have 1 minus 1/2 all times sine of 2 theta, which we just said was 2 sine theta cosine theta. So here our 2's cancel. And we're left with 1 minus sine theta cosine theta. Which I'm not sure how I'm going to get it to look like the following. So maybe we need a sine theta plus cosine theta in the denominator. So I'm wondering if we multiply both the numerator and denominator, multiplying this by a fancy 1. Sine theta plus cosine theta. So when working through these identities, it's good to look at where we're trying to go, and that can kind of help you and guide you where to go. So I need to know by working on the left-hand side, the right-hand side has that sine theta plus cosine theta in the denominator. So let's distribute here. So if I distribute it in my numerator, I have this 1 sine theta, which is sine theta, plus 1 times cosine theta, which is cosine theta. Now distributing the sine theta, cosine theta. So sine theta, cosine theta, so it's minus sine squared theta, cosine theta. So distributing negative sine theta, cosine theta to cosine theta, this gives us minus sine theta, cosine squared theta. And this is all over sine theta plus cosine theta. So let's think about, I know in that numerator, I have a sine cubed theta and a cosine cubed theta. If we go back to another identity that we know that cosine squared theta plus sine squared theta equals 1. So if I manipulate maybe the sine squared theta to look like have cosine squared theta in that. So I could do that by rewriting that identity above as sine squared theta is equal to 1 minus cosine squared theta. I can do the same thing by solving for cosine squared theta. We can also write cosine squared theta as 1 minus sine squared theta. Let's go back in and rewrite those. So we have sine theta, bringing down sine theta, plus cosine theta, minus sine squared theta, but sine squared theta we just said was the same thing as 1 minus cosine squared theta, all times cosine theta, minus sine theta, all times cosine squared theta, but rewriting cosine squared theta, that's the same thing as 1 minus sine squared theta. All over our numerator of sine theta plus cosine theta. So let's distribute. Before we do that, let's bring over our sine theta plus cosine theta. So I'm going to distribute negative cosine theta. I'm going to carry the negative with me. So a negative cosine theta times this 1 here is minus cosine theta. Negative cosine theta times negative cosine squared theta. Negative times negative is positive. So plus cosine cubed theta. And so we're going to do the same thing here. Now we're going to distribute negative sine theta inside the parentheses. So negative sine theta times 1, so that's minus sine theta. And negative sine theta times negative sine squared theta, that's plus cosine or plus sine cubed theta. All over this sine theta plus cosine theta. So notice things cancel out really nicely, and it's left with what we need. Sine theta minus sine theta here cancels. Cosine theta minus cosine theta cancels. And what we're left with is cosine cubed theta plus sine cubed theta. I'm going to just rewrite the order, and I can do that because it's commutative. So this is the same thing as sine cubed theta plus cosine cubed theta, all over sine theta plus cosine theta. So we showed what we wanted to do. So working on the left-hand side, we got our right-hand side of the equation. So looking at one more example, secant of 15 pi over 8, using the half angle identity to find the exact value of this. So 15 pi 8 is not an angle that we know. So we want to, and it told us to use the half angle. So we're going to manipulate this and multiply it by 2 over 2. So since it's a fraction that we're keeping in the numerator, think of it as when we're multiplying it by 2, I think it's helpful to write that 2 as 2 over 1. And then the 2 in my denominator there. So when I do that and I multiply this 2 over 1 times that 15 pi over 8, I can reduce my fraction. 2 goes into 8 4 times. So this is secant of 15 pi fourths all divided by 2. So looking at this, I would first, I would probably rewrite this as cosine. Secant is the same thing as 1 over cosine. So looking at this, this is the same thing as 1 all over cosine. 15 pi fourths all divided by 2. So let's figure out what 15 pi fourths is. So I know that 4 goes into 15 approximately 3 times. So let me just write this over here. So 15 pi fourths. So 4 goes into 15 pi 3 pi times. So that's 12 pi. And so 12 pi, 15 pi minus 12 pi, I'm left over with a 3 pi over 4. So looking at that, if I did 3 pi as my rotation, well, one circle is 2 pi. Coming over here to the negative x-axis, that's another pi. So that's 3 pi, and now I need a 3 pi fourths. Well, 3 pi fourths, that's a little less than pi. It's pi fourths less than pi. So that's going to get me into the 4th quadrant with a reference angle of pi fourths. That's going to help me when I go back to evaluate. So I have a half angle for cosine. So let's rewrite that using the half angle formula. So we have 1 in our numerator all over plus or minus 15 pi fourths over 2. Okay, so this is plus or minus the square root of 1. It's a cosine half angle, so it's plus cosine of my numerator, 15 pi fourths, all over 2. So let's determine, is that plus or minus in front of the radical? Well, let's go back to our original 15 pi eighths. 15 pi eighths. 15 pi eighths. Well, I know 16 pi eighths is 2 pi. That would be 1 full revolution. So we're not quite up to 1 full revolution. We're less than pi eighths to 1 full revolution. So that means I'm in quadrant 4. I'm dealing with cosine, secant, which is 1 over cosine. Secant in quadrant 4 is positive. So remove this positive. Okay, so now we can continue evaluate. So we have 1 all over the square root of 1 plus cosine of reference angle pi fourths, that's root 2 over 2. We're in quadrant 4, cosine is positive. So plus root 2 over 2 all over 2. So clearing the fraction underneath the radical, we can multiply by 2 over 2. Distributing that 2 over 2 in the numerator of the denominator of that fraction. it gives us 2 plus root 2 all over 4. So this is 1 all over root 2 plus root 2. That's all over square root of 4, which is 2. So invert multiply. So we get 2 all over the square root of 2 plus root 2. So rationalizing the denominator. So notice it's only one term right now in the denominator, that main radical. So we're going to multiply by that main radical, root 2 plus root 2, all over root 2 plus root 2. So in the numerator, I have a 2. It's not under a radical, so I can't distribute underneath that radical. So 2 times the square root of 2 plus root 2. All over, well, we multiplied the denominator so that that's like a square, and it would cancel that radical out. So we just get what's underneath the radical, 2 plus square root of 2. We still have a radical in the denominator, but we now have 2 terms in that denominator. So the trick is to multiply by that conjugate, changing the sign in between those 2 terms. So 2 minus root 2, all over 2 minus root 2. So keeping it in factored form, in the numerator, I have 2 square root 2 plus root 2, all times 2 minus root 2, all over, this is a difference of squares in my numerator or denominator. So we have 2 times 2, which is 4, minus root 2 times root 2, which is 2. That's going to give me 2 in the denominator. And that 2 in the denominator is going to cancel with this 2 in the numerator. And so we're left with our final answer. Reduced form is the square root of 2 plus root 2, all times the quantity 2 minus root 2.